a model that can compute this, right? We want to create a system dynamics model that describes or that can solve this set of equations. So there, we have three stock variable or level variable, which is S and I and R. That's an accumulation of number of people in that compartment, right? So we have three stock variables here. So let's just create those three stock variables. So susceptible and infected and recovered. Okay. So I just created three level variables, and then I know I need a bunch of auxiliary variables. So let's start with the total population. And contact rate, not wage. Contact rate. And infectivity. And recovery rate. That's pretty much it, right? So here I have as a auxiliary variable constant in this case, beta, alpha, and gamma. That's all I need. Alright, so now there are the people moving from susceptible to infected, so that can be indicated as a flow from S to R. Let's say that's being infected, and from infected to recovered. Okay. So, and now back to this. So this dsdt is essentially what I just put in here, being infected. That's the rate, right? Rate of change. And that's a negative, let's not, we're not worried about negative yet. Beta, alpha, I, S over N. So, what I do is, okay, I know that being infected is a function of beta, alpha, and S is automatic, but S, I, and N. Right? So I know that this rate is function of beta, alpha, I, S, N. Right? And for being recovered, I know that this is a function of gamma and I. And last one, I know the total population is a function of S, I, and R. Okay. So I just make the connections to indicate the functional relationships that I have over here. And the last step is to specify the equations that goes behind this functional relationship there. Okay, so let's start with susceptible. So the susceptible, the level variable susceptible is by, the software already know that I'm taking people out of the susceptible population, so it automatically has this. Susceptibles is integration of negative being infected, which makes sense, right? Susceptible is integration of the flow out of the susceptible. That's fine. And the initial value, let's say 990. Okay. And units, it's a number of people, so let's just say people. And I say, okay. And being infected, equation. So being infected, as you can see, it has all the variables that I connected to the being infected variable there. So being infected is the rate, which is beta contact rate times infectivity times infected population times susceptible population divided by total population. That's beta alpha I S divided by N. That's what I have here. And the unit is people per, say, day. I say, okay. So I specified this. And infected. This only has a minus being recovered, but I need an inflow. Sometimes it does automatically update that, sometimes it doesn't. So being recovered, the inflow is being infected, outflow is being recovered. So infected is an integration of being infected minus inflow minus outflow. Initial value, let's say 10. There are 10 initially infected people in the population. So PPL, people, unit is people, and okay. And being recovered, that's the rate, which is simply infected times gamma times infected. Right? So recovery rate times infected. So unit is again PPL per day, since it's a rate. And recovered is integration of inflow. And the unit is people. Initial value is 0. So I specify this. Total population, I also need to specify that. Total population is simply the sum of SIR. And unit is people. And contact rate. Let's give a contact rate. How many people we meet a day? Say we meet on average 5 people a day. So this is people per day. How many people you meet a day? And infectivity is what's the chance of real infection given the infectious contact, let's say 0.5. So I'm sick and I meet 2 people, then I can infect 1 person. Okay? So this is a person, people over people, so unit is 1, suppose. And recovery rate, say if you get sick, you are sick for say 7 days. So recovery rate is 1 over 7. It's 1 over. So I specify all the equations and constants behind the scene. Now I should be able to run the model. So let's just check. First, a unit check. Unit error recovered. What's wrong? So being infected, So I guess I'm missing one people unit somewhere, probably contact rate. Well, let's just ignore that for the time being. And check model, model's okay. And run the model. If we run the model, it ran. Since it's a deterministic differential equation, it doesn't even take any time. So let's see what we've got there. So this is, I did something wrong here. So more or less it looks fine. Infected goes up and down, the susceptible goes down, and the recovered goes up, but you can't go negative, right? So somewhere I made an error in the model. It's going to be tough to identify where I made the errors. One way of identifying the error is by looking at let's see what we have done wrong. So let's look at the susceptible susceptible minus being infected. That's fine. Initial 990. You need people. You need to help me.